Hello everyone, welcome back to Diksha Karnataka YouTube channel, and today I am going to bring you the top 50 most important questions that includes 2 marker questions and derivations. So total we are going to do 42 marker and 3 marker questions and 10 very important derivations. All of them are collected across several years of your previous year questions, some important questions from your model question paper. So all point of view are covered, and these are the most important questions that might come in your PU board exam with some intuition. I am telling you, if you watch this video, 40 marks from your PU board exam will be guaranteed, and other than 40 marks, for example, MCQs, then fill in the blanks, then numericals that you have to solve. We have done videos for every one of them, so please do check that out if you have not yet checked any of them, right? This is for the weaker section of the students, those who are not able to score well with MCQs, those who are not score well with the numerical section. So there is no MCQ, no numerical questions in this lecture, only 2 marker, 3 marker and derivation. So you can consider this to be a last minute suggestion, or you can consider it to be a last minute passing package. So if you watch this, definitely 40 marks will be sorted for you. Without any delay, let's start with today's lecture. We'll go through this lecture quickly because obviously we have a lot of questions to cover. 50 questions is not small. So first, state and explain Coulomb's law in electrostatics. Most common, most asked question statement. Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the 2 charges and inversely proportional to the square of the distance between them. It acts along the line joining the charges. So this is the first statement, and then you have to explain it. This is the statement, state and explain. The explanation is there. What is explanation? That you have to write that, you have to draw the diagram as well. 2 charges Q1, Q2 separated by a distance r. Then mathematically we can write F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square, where Q1 Q2 are point charges, r is the distance between Q and Q2, and epsilon naught is the permittivity of free space. So this is the Coulomb's law, this is the formula, okay? And if you write it, state Coulomb's law generally comes as a 2 marker question. State Coulomb's law and write mathematical expression. If they ask you explanation, explanation means you have to write everything, and you have to draw the diagram as well. For that you get 3 marks, okay? So this is up to 3 marks, is a very important question. Now let's move on. Write any 3 properties of electric charge. Another very common question asked across the years, okay? 2 properties, 3 properties. 2 properties obviously 2 marks, 3 properties is 3 marks. So 2 property means 2 marker question, 3 properties means 3 marker question. All sorts of possibilities are there. So let's see. Additivity of charges. Charges are additive in nature. Quantization of charges. All charges are integer multiple of smallest charge E. E is obviously the charge of an electron. Conservation of charges. Total charge in an isolated system is conserved, okay? So this is the 3 properties of charges. Next, 3 properties of electric field lines. Another very common question. Students are always waiting for such questions. Let's see. Electric field lines may start from positive charge and end at negative charge. 2 electric field lines are never intersect each other. Electrostatic field lines do not form any closed loops. So these are the 3 important points for electric field lines. Now let's move on. State and explain Gauss law of electrostatics. Another very common question. If it is not coming as a single question, it sometimes comes as a part of a 5 marker question, okay? State Gauss's law of electrostatics, okay? So that is also possible. So sometimes this is a 2 marker question usually, but it can come as a 1 marker question as the beginning of the Gauss's law theorem related questions, okay? So Gauss's law states that the total electric flux passing through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. This is the statement. If they ask you the state Gauss's law only in the 5 marker section, then only this much is sufficient. But if it is asked as a 2 marker question, then you have to write the explanation as well. Phi is equal to Q by epsilon naught. You can draw a diagram. So this is a charge Q enclosed by some surface S, then E dot ds equals to Q by epsilon naught. Q is the total charge enclosed by the surface S. Okay. What is an equipotential surface? What will be the shape of equipotential surface corresponding to a single point charge? So let's see, any surface which has the same electric potential at every point is called equipotential surface. The shape of an equipotential surface is spherical by a single point charge. You can draw the diagram as well. So you have to show concentric spherical spheres. Okay, this is the concentric spheres showing you the shape of the equipotential surface. Now next question. On what factors does the capacitance of a parallel plate capacitor depends? Another very common question. So parallel plate capacitor C equals to A epsilon naught by D. So it is directly proportional to area, inversely proportional to the distance between the plates, and directly proportional to the dielectric constant. So commonly there is a K as well. So K is the dielectric constant. So it depends on, obviously C is directly proportional to area. It is inversely proportional to the distance between the plates, and it is directly proportional to the dielectric constant. Okay, so these are the 3 points. So in case it is asked as a 3 marker, you have to write all 3 points. If it is asked as a 2 marker, only 2 points are sufficient. Now write 2 properties of equipotential surface. It is again 2 properties means 2 marker, 3 properties means 3 marker. So all possibilities are there. No work is done moving a test charge over an equipotential surface. Electric field is always normal to the equipotential surface at every point. No two equipotential surface can intersect with each other. So again same, the most common property of all the things that you study, properties of field lines, properties of equipotential surface, properties of magnetic field lines. So this is the most common property. All the students remember it, write it correctly, but other properties they might forget. So you have to remember these points. Now if you are not satisfied watching it once, you can watch it twice. Okay, you can watch it in a 2x speed. I am going in a very fast anyway, so if you are going in a 2x speed, make sure this is your second time watch. First time watch it in a 1x speed. Okay, later on once you are finished, then you can watch it as a 2x speed, so that you can remember the values. The PDF of this lecture will be given in the WhatsApp channel. So if you have not joined our WhatsApp channel, the link of this is given in the description. Also, if you have not yet subscribed to our channel, don't forget to subscribe to our YouTube channel as well. Now draw equipotential surface for a positive point charge, a uniform electric field. This is one of the previous year question. So positive charge, it will be like that, point charge, spherical surface. This is answer A. And for answer B, constant electric field or uniform electric field, we know that they are planes. So you have to draw the planes parallel to each other. Okay, and the electric field lines are passing like that. Let me draw it a little bit clear. So electric field lines will be parallel, and as you know, the equipotential surface is always normal to that, so you can draw the equipotential surface like this. Okay, so this will be your equipotential surface, right? This is for the uniform electric field or constant electric field. This is the type of equipotential surface, right? Use compass and scale. Don't use normal hand like me. Okay, so that your diagram is perfect. These are very scoring questions, so don't lose marks because you are too lazy, right? Now give 3 results of electrostatics of conductors. So inside a conductor, electrostatic field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation. This is from one of your model question paper, very modern question. But it is tend to come in some of the district papers, that is your pre-board papers. This question came, so that is why I thought maybe this will come in your board exam. So this is a very high chance of coming as well. So this is a 3 mark question, but it can come as a 2 marker question as well. Okay, now derive the relationship between electric field and electric potential due to a point charge. Very common question. So first you have to draw this diagram where you have to show this thing. As I mentioned multiple times, your lower point will be low potential, higher point will be a lower potential. Don't follow the NCERT derivation. If you are following NCERT derivation, there is a high chance you make a mistake in the calculation. Okay, so how to do that? Electric field always points from higher potential towards lower potential. That is the starting point. The distance is say dl. The distance, say dl. This is V minus dV. Then what is the work done? First of all, it is an uniform electric field. Because the distance is very small, you can consider that the electric field is constant throughout between these two electropotentials. So what is the, if you keep a charge small q here, what is the force acting on this charge and what directions? Positive charge, so it will experience a force in the direction of electric field. And what is the magnitude of the force? The force will be q into electric field. That is the definition, right? So for a charge kept in an electric field will experience a force q into E. Now if you move it by a distance, say dl, then what is the work done? So the work done will be given by force times displacement. That is the definition, mechanical definition of work done, right? So mechanical definition of work done, very simple derivation. If you just practice it 2 times, you can even solve it yourself. So this is the first stage, first case where we have calculated the work done using mechanical definition. So this is part 1. What is part 2? Part 2 is where we will do the same thing, but now we will use the electrical definition of work. What is electrical definition of work? Electrical definition of work says that it is nothing but the charge times the potential difference. What is potential difference? Final potential minus initial potential. So it is moving from a potential V to V minus dV. So the work done is given by Q into V minus dV minus V. So this is one term, this is the second term. Okay, now if you do the mathematics, obviously this V will cancel, you will get the work done to be minus Q dV. There is a minus sign on the dV, so that minus sign will come out. Now work done we have calculated using 2 processes. Now is the work done in these 2 processes will be different? So from the conservation of energy, obviously if you are calculating work done from one process, the work done from the second process should be same. Okay, so work done cannot be different in 2 different processes, so definitely Q into dV must be equal to Q into E dl. So what we have done, we have compared equation 1 and equation 2. Both are dWs, both should be same, right? That is the mathematics. So from there we can see that Q cancels and E becomes minus dV by dl. Okay, so this is the relationship between electric field and electric potential. Okay, this is the relationship between electric field and electric potential. Right, now what is the significance of this negative sign? The negative sign signifies that electric field points from higher potential to the lower potential. That is the meaning of this negative sign. Okay, easy, cool. Let's move on to the next derivation. The next part, obviously, write the expression for drift velocity in terms of current. Explain the terms used. Now, from the current, there are a lot of possible questions are there, but this is the one of the most commonly asked question. So, obviously, we are covering all common questions, most probable, not super difficult questions, so that anyone who is watching this video can score 40 plus. That is my target. Okay, anyone, even if he is a failure, he has not passed any of the exams. If you watch this video, he should still score 40 plus marks. That is my target. So I is equal to NEA VD. This formula you have to remember, very important formula. I equals to number density charge of an electron into area, NEA into VD. VD is the drift velocity. Okay, so I equals to NEA VD. From there you can calculate VD equals to I divided by NEA. Obviously VD is drift velocity, I is the current carrying by the wire, and N is the number density of electron. Number density means if you consider a small volume, Okay, this volume is say 1 unit volume. Whatever the unit volume, whatever is the number of electrons in that unit volume, free electrons, okay, number of free electrons in that unit volume, that is the number density. That is called the number density of electrons. E is charge of one single electron. A is the area of the cross section of the conductor. So A is the area of the cross section, okay, through which current I is flowing. Okay, so this is very, very simple, easy answer. Define drift velocity and mobility of free electrons in conductors, or define mobility, mention its SI unit. So both are 2 marker questions. Either they will ask you both definition and or they will ask you to define mobility, mention its SI unit. Sometimes they might ask you the relationship between drift velocity and mobility. That is also might come. So let's see. Drift velocity is the average velocity with which the free electrons drift under the influence of an electric field. Okay, so when you are under the influence of external electric field, the electrons cannot stay stable. They start moving slowly opposite to the electric field, and that is called drift velocity. The mobility of free electron is defined as the drift velocity of electron per unit electric field applied. So mobility is, if they ask you the relationship between mobility and drift velocity, mobility is drift velocity per unit electric field, that is Vd by E. Okay, so this is the relationship. In case they change the question slightly and say now you have to answer what is the relationship, then he will say, sir, you have done everything, but you have not taught us the relationship. So I am giving you that as well. The SI unit of electron mobility is meter square second inverse V inverse, or meter second inverse Newton inverse Coulomb. So it is mainly meter second inverse Newton inverse Coulomb. Okay, meter per second is the unit of electric field. Newton inverse Coulomb is divided by electric field. So you can say, okay, I know this relationship, I want to write the unit. How to write that? So velocity is basically meter per second, right? And electric field is Newton per Coulomb, right? So units will be definitely this. So if you don't know, you can leave it like this. This is also fine. Otherwise, what you have to do, you have to, so meter is there, Coulomb is altogether division, so it will go up, and second inverse Newton inverse. This is the unit. Okay, another unit is meter square second inverse volt inverse. That also you can write, because in this case the unit of electric field is taken in volt. Anyway, let's move on. Let's not complicate the things. Mention 2 limitations of Ohm's law. Another important question. Ohm's law is applicable only if all the physical conditions remain same. Ohm's law is not applicable at very low and at very high temperature. Okay, Ohm's law is not applicable to non-ohmic devices like semiconductor devices, discharge tube, etc. Right? Now question number 14, give any 2 differences between current and current density. So current is defined as the amount of flow of electric charge per unit time. Current density is the amount of current per unit area. Unit of current is ampere, unit of current density is ampere per meter square. Very, very important. So these are the very 2 important difference of current and current density. Okay, so current is represented by the symbol I, and current density is J, which is nothing but I by A. Okay, also it is sigma E, whereas current is equal to V upon R. Okay, from Ohm's law, current is equal to V upon R. From Ohm's law, current density is equal to J equals to sigma E. So this is also another difference if you want to write. Now, show the variation of resistivity with absolute temperature for nichrome. So how nichrome changes? First is nichrome. Okay, nichrome, for nichrome the resistivity changes with absolute temperature is almost constant. It stays very it does not change very highly, so it is almost constant with small slope. So this is the change of resistivity of nichrome wire. It is a straight line. Remember that it is a straight line. Okay, not any curved line. and the slope is very small. Okay, whereas for silicon, if you consider silicon, it is a semiconductor. So with temperature, how does its resistivity changes? Its resistivity decreases. So it is the resistivity graph for silicon. Okay, so remember that nichrome remains almost constant. It is not exact constant, flat line. Okay, if you change the temperature very high, then slowly its resistivity increases by small amount, but for silicon it is decreasing. That is very, very important. Okay, for normally if you consider say copper, okay, for copper, if the same question was asked for copper, okay, the resistivity will increase very sharply. Okay, so this is the difference between copper and nichrome wire. Okay, copper even it will increase very, very sharply. The slope is very, very high, whereas for nichrome the slope is very, very small. Okay, so you should know all the way how it will be different. Now next question. When does a current carrying conductor placed in an uniform magnetic field experience a maximum force? Or current carrying, you have a current carrying conductor, you place it in a magnetic field, it will experience a force. When it will be maximum? So maximum will be when the current flowing is the perpendicular to the direction of magnetic field. So if current is perpendicular to the direction of magnetic field, then the force is maximum. Minimum force when the current is flowing in the same direction of magnetic field. So magnetic field and current both are in the same direction. This will be the minimum force. Okay, next question. State and explain Biot-Savart's law. Write its vector form. So Biot-Savart's law, to draw to state and explain Biot-Savart's law, first of all you have to draw this diagram. Very, very important. Okay, and what else? You have to mention that the magnitude of the magnetic field. Magnitude term is important. The magnetic field, obviously we are trying to measure magnetic field. Biot-Savart's law talks about magnetic field. Okay, at any point P. So here it is our point P where we are trying to measure the magnetic field. It depends on four things. What are those? Directly proportional to the strength of the current. So obviously whatever current I is flowing in the circuit, it is directly proportional to that. Directly proportional to the length of the current element. So whatever current element you have considered, here we have considered this much dl length. So it is directly proportional to dl. Directly proportional to sine of the angle between the current element and the line joining the midpoint. So if you join the midpoint of the element, so element is somewhat length, right? So if you join the midpoint of the element with the point and the angle that it makes with the element. So element will be, how to find that? If you extend the element in both sides, okay, and join the midpoint of this element with the point P, then it will make some angle. That angle is called theta. So it is directly proportional to the angle, sine of this angle. That is, it is directly proportional to sine theta. So proportional to sine theta. What else? Inversely proportional to the square of the distance between the current element and that point. So square of the distance, so distance is r, so it is inversely proportional to the square of the distance. Okay, here it is directly proportional to dl, here it is directly proportional to I. And if you combine them, the equation becomes dV, that is magnetic field, is mu naught by 4 pi, okay, I dl sine theta by r square. This is the mathematical form for Biot-Savart's law. Sometimes they might ask you what is the mathematical form. Now, but its law itself is a 3-marker question. So generally this is not asked unless they only ask you what is the mathematical form of Biot-Savart's law, explain the terms. Then you have to write it down and explain the terms. What is the Lorentz force? Write expression and explain the terms. So Lorentz force is the force between when you keep when a charged particle moves in an electric and magnetic field, it experiences a force that is called Lorentz force. Now expression is, there are two forces. So obviously one is electric force, which is Q into E, and there is a magnetic force which is Q into V cross B. This is a vector quantity and the law is a vector law, so you have to write it in terms of that. So total force, this is called Lorentz force, is basically electric force plus magnetic force. So this is basically Q into E plus V cross B. E plus V cross B, right? This is the Lorentz force. Okay, now how can a galvanometer be converted into a voltmeter? Explain with the diagram. So obviously a voltmeter should be very high resistance as it's connected parallel to the circuit. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with it. This way overall resistance of the voltmeter remains high. So the diagram is this. So here in case of voltmeter you have to apply a very high resistance in series. Okay, this is a very high resistance and the current in the galvanometer Ig can be given by V by Rg plus R. Okay, so this is the major voltage and this is the formula that you can write here. Next is how can a galvanometer be converted into an ammeter? Explain with the diagram. Also very important question. An ammeter should have a very low resistance as it is connected in series with the circuit. So first line in both cases, first line should be how we are connecting the ammeter or voltmeter. Ammeter is measuring current, so it should be connected in series. Voltmeter is measuring voltage which is across something, so it is connected in parallel. So if you are connected in parallel, then the resistance will be in series. If this is connected in series, the resistance which will connect, the external resistance, that will be in parallel. So in case of ammeter, it is connected in parallel. That's what student gets confused with. Okay, so ammeter is where a low resistance value is connected in series, and voltmeter high resistance value is connected in series. Okay, for ammeter it is low value resistance connected in parallel, not series. My mistake. So this is achieved by connecting a suitable low resistance S in parallel with a galvanometer. This way the overall resistance of the ammeter remains low and the galvanometer is converted into an ammeter. Okay, you can even calculate what is the value of this S. So current through this is Ig. Okay, current through this is I minus Ig. Total current that you are measuring is I, that is the maximum current you can measure. Okay, so from there you can say that Rs into I minus Ig, that is voltage drop across this, should be voltage drop across this, that is G into Ig. Okay, and then you can calculate Rs. Rs will be G into Ig divided by I minus Ig. So this depends obviously on the maximum value that you want to measure. Here the I is the maximum current that you are measuring. Ig is the maximum allowed current through the galvanometer. If it is exceeds that value, then the galvanometer will burn, right? So this is how it works. This is the formula for the resistance that you need to want to connect. Now write the three differences between diamagnetic, paramagnetic or ferromagnetic material. So this is again, as I said, it is a combined question. There are three different questions is possible from this. Difference between diamagnetic, paramagnetic, difference between diamagnetic, ferromagnetic, difference between paramagnetic and ferromagnetic. So this is a combined question. So even though it is given as a single question, you can consider it to be a three question. So if you take a snapshot of this, or if you download the PDF of this and remember it, obviously points are very common. First is magnetic behavior, how they behave. So diamagnetic substances are weakly repelled, paramagnetic substances are weakly attracted, whereas ferromagnetic substances are strongly attracted. Okay, magnetic susceptibility is small and negative, it is small and positive, it is large and positive. Okay, effect of magnetic field, it weakly repelled by the magnetic field. It is induces a magnetic moment in the opposite direction of the applied field, induces a magnetic moment in the direction of the magnetic field, induces a strong magnetic moment in the direction of the magnetic field. Okay, so that is also very, very important. You can write the relative permeability as well. Relative permeability is basically 1 plus chi, so that is also very, very simple. Okay, so it will be small but positive, it will be slightly bigger, it is small but less than 1. Okay, in case of diamagnet, it is small but less than 1, it is small and greater than 1, it is very, very greater than 1. Okay, that is the 0 will be replaced by 1. That is another point if you want to remember. Write any 3 properties of magnetic field lines. Another common question, easy question. The magnetic field lines form continuous closed loops. Now it is forming continuous closed loops. In case of electric field lines, the loops are not closed. Okay, they are open. Magnetic field lines are continuous and closed. So that is the difference. The tangent to the magnetic field lines drawn at given point represent the direction of the net magnetic field at that point. Larger the number of field lines crossing per unit area, stronger is the magnitude of the magnetic field B. The magnetic field lines does not intersect. So same point, very common point, all the students' favorite point. Now, state and explain Gauss's law in magnetism. So Gauss's law for magnetism is the net magnetic flux through any closed surface is 0, that is B dot ds equals to 0. Physical significance, magnetic monopoles do not exist, that is the magnetic field lines always form closed loop. These are the 2 physical significance. Now next question, state Faraday's law and Lenz law of electromagnetic induction. Okay, so what is the Faraday's law? Faraday's law says that the time rate of change of magnetic flux through a circuit induces EMF in it. Lenz law says the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it. Okay, derive the expression for motional EMF induced in the straight conductor moving perpendicular to a uniform magnetic field. Okay, so first we have to draw this diagram where this frame is compulsory. This is a moving wire frame which is moving with the velocity v. The distance at some time is x. This height is L, which is fixed. Magnetic field into the page of the paper. Obviously cross means into the paper. I told you cross means into the paper because you want to hit it. Cross means the target where you want to hit, and circle means it is coming out of the paper. Okay, so magnetic field is into the page of the paper, which is B. Now first of all, what do we have to do? We have to find the flux linked with this portion. How to find the flux linked with something? So flux, magnetic flux or electric flux, whatever it is basically magnetic field into area. If it is electric flux, electric field into area. Okay, flux is always field into area. Okay, now magnetic field is constant B, so we do not need to worry too much about this magnetic field B. Area is what we are concerned about. What is area? Area, this is what is the shape? This is a rectangle. So what is the area of a rectangle? Area of the rectangle is length into breadth, right? Area of a rectangle is length into breadth, that is L into X. Now what is the induced EMF? Induced EMF is d phi b by dt. Okay, d phi b into dt. So d dt of b L x. Okay, d dt of BLX. Now B is constant, L is constant, L is not changing, only thing that is changing is our X, so it will be dx by dt. Okay, so what is dx by dt? So it is the rate of change of distance. Rate of change of distance is nothing but velocity, so it will be BLV or BVL. Okay, so the induced EMF is BLV. This is the magnitude of the induced EMF. Okay, this is the magnitude of the induced EMF, also called motional EMF. Okay. Next question. Explain briefly the Coil-Magnet experiment to demonstrate the phenomena of electromagnetic induction. Another question which sometimes comes when a magnet approaches the coil. So first of all, you have to draw this diagram. There is a coil, there is a galvanometer connected here. This is not a battery, remember that. This is a galvanometer, this is a magnet, north south. It is shown here, and there will be an arrow. Arrow means the magnet is moving towards the coil. Okay. So when the magnet approaches the coil, the galvanometer needle deflects. So when the magnet is approaching the coil, the galvanometer deflects, indicating a current is induced. So that what is the meaning of deflection of galvanometer? Deflection of galvanometer means there is a current which is flowing through this, but initially there was no current. So this current which is came into the circuit because of the motion of the magnet is called induced current. Okay, so we can say that there is a current induced in the coil. Okay. When the magnet is pulled away, now if you take the magnet away from the coil, the needle deflects opposite direction, showing that the current reverses. So no current is induced when the magnet is stationary related to the coil. So when you are taking this in this direction, there is a current. If you take it in the other direction, there is a current, but in the opposite direction. And if the magnet is stationary, no current is flowing in the galvanometer at all. Okay. Conclusion: a current is induced in the coil when the magnetic flux through the coil changes. This confirms Faraday's law of induction, and the direction of the current flows follows Lenz law, opposing the change in the magnetic flux. Okay. Now mention 2-3 uses of applications of Polaroids. Another super important question. Polaroids are used to control the intensity in sunglasses, window panes, etc. Polaroids are also used in photographic cameras and 3D movie cameras. They are used in 3D movie glasses as well. So 3D movie cameras which records the movie uses Polaroids, and 3D movie glasses which you wear to watch 3D movies are also Polaroids. Okay. Now mention Einstein's photoelectric equation and explain the symbol. Okay, so this sometime comes as a 5-marker part of the 5-marker question. So this is a must do question. So h nu is equal to 5 plus half mv square. This is the Einstein's equation. There are different forms to the same equation, but this is the main equation. H nu equals to 5 plus half mv square. H is the Planck's constant. Frequency of the incident light is nu. Phi is the work function of the metal, m is mass of the electron, and v is the velocity of the ejected electron. Okay, this is the easiest formula. Next, write 3 features, properties of nuclear force. So nuclear force is much stronger than the Coulomb force acting between the charges or the gravitational force between the masses. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. Nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately the same. That is, the nuclear force does not depend on electric charge. So write 3 limitations of Bohr's atomic law. So Bohr model is applicable to hydrogenic atoms only. Next, the model is unable to explain the relative intensities of the frequencies in the spectrum, and the model does not explain the fine structure and splitting of spectral lines. Okay. Give Einstein's explanation of the photoelectric effect and write Einstein's photoelectric equation. So photoelectric equation we have already written. Let's see the Einstein's explanation. Einstein suggested that each photon of light has energy proportional to its frequency nu, given by E is equal to h nu, where h is Planck's constant. When light shines on a metal surface, photons transfers their energy to the electrons in the metal. Any energy from the photon exceeding the work function becomes the kinetic energy of the ejected electron. Now, give any three results of the experimental study by photoelectric effect. It is also called Hallowell-Leonard's observation. So, you see the question on three experimental observation, three observation of Hallowell-Leonard. So, these are the same question. So, for a given metal, no electrons are emitted if frequency of the incident light is below a certain minimum value called the threshold frequency, regardless of the intensity of the light. Very important first point. Second point, now these are descriptive questions, so you have to memorize it little bit, but they are very frequently asked, so you have to remember it anyway. Photoelectric emission occurs without any noticeable delay after the light strikes the surface, even for a very low light intensities. The maximum kinetic energy of the emitted electrons increases linearly with the frequency of the incident light above the threshold frequency. Okay, what is meant by photoelectric effect? Defined work function, defined threshold frequency. So the photoelectric effect refers to the phenomena where electrons are emitted from the surface of a metal when light of a certain frequency or light higher shines on it. These emitted electrons are called photoelectrons. Next is the work function phi is the minimum energy required to eject an electron from the surface of the metal. It is property of the metal and typically measured in electron volts eV. Okay, the threshold frequency nu naught is the minimum frequency of the incident light required to cause the emission of electrons from the surface of a metal. For light with frequency below nu naught, no electrons are emitted regardless of the light's intensity. Okay. How can a semiconductor diode be forward biased? What happens to the width of the depletion region when the forward bias voltage is increased? So, as a semiconductor diode is forward biased, when you connect the positive terminal of a power source like a battery to the p-type side of the diode and the negative terminal to the n-type of the battery, the setup holds up to overcome the potential barrier created by the depletion region and allows the current to flow through the diode. As you increase the forward bias voltage, the depletion region becomes narrower and slowly disappears. So what is forward bias? You have a diode. Diode is like a block like this. So there is a depletion region. Here it is a p side, here it is a n side. So if you connect the p side to positive and n side to the negative, then there is a current flows in the circuit. This is called forward biasing. And in the forward biasing, the depletion region slowly decreases and it slowly vanishes. It becomes zero. What are intrinsic and extrinsic semiconductors? So intrinsic semiconductors are those pure semiconductors are called intrinsic semiconductors. The presence of charge carriers, electron and holes in an intrinsic semiconductor is an intrinsic property of the material, and these are obtained as a result of thermal excitations. So number of electrons and number of holes are same. They are intrinsic properties and it can only be obtained by exciting it thermally. Okay, whereas what is extrinsic semiconductor is the number of charge carriers can be changed by doping of a suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are two types, n-type and p-type. If you dope with the pentavalent, you get n-type. If you dope with trivalent, you get p-type. There is sometimes difference between p-type and n-type is also popular, but I am not going to cover that. Name the objective used in a refracting type telescope and reflecting type telescope. Objective is very important. Okay, objective means whoever is facing the object, that is called objective. If you have done laboratory for biology experiment, then you should know when you are watching this, whoever is closer to your eye is called eyepiece, whoever is facing the object is called objective. Okay, similarly the telescopes are also used to observe distant object. Telescope are distant object, microscopes are closer object, closer but small object. Telescopes are distant but bigger objects. So telescopes generally uses convex lens for refracting type and concave mirror, very important, concave mirror for reflecting type. Reflecting means which is reflecting. It is a concave mirror for reflecting, convex lens for refracting. Write the two conditions required for total internal reflection. Another important question. Light must travel from denser to rarer medium. The angle of incidence must be greater than the critical angle. Okay. Next question. Write two uses of ultraviolet radiation. So UV radiations can be focused into very narrow beams for high precision applications such as LASIK. UV lamps are used to kill germs in water purifiers. Okay. Next is the name the electromagnetic waves used for the following application. Radar system used in aircraft navigation, the remote switches of household electronic systems such as TV. So in radar system we use microwaves. In infrared switches, that is your household systems such as TV remotes, used infrared radiation. Next is what is the displacement current? Give the expression for it. This is also from electromagnetic wave chapter. Displacement current is the current due to changing electric field is called displacement current. This expression is ID equals to epsilon naught or d phi E by dt. So let's continue with the lecture. Derive an expression for the electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss's law. So this is the most common question from this chapter, from most of the last few PYQs, whatever I have seen. If there is a question from Gauss's law, this is the question. Obviously they ask state Gauss's law first, then they ask this question. So this is most common question, and in case you need to answer this question, if you don't get this question in first paper, maybe those who will repeat in future, they will definitely get this question. Okay, one of the three papers this question will definitely come, but I hope you will clear your physics paper in the first attempt. You will score more than 40. Obviously that is my dream. So first you have to draw a diagram like this. Positive charge, show positive charge, that is sufficient. Negative charge, we want to try to be positive, so that is why it is positive. The distance is r. Okay, the point that where we are trying to find the electric field is P. So first we have to construct a Gaussian surface. Okay, Gaussian surface of radius r, and say the length of the cylinder is lambda. Okay, the charge per unit length is charge per unit length is lambda, and length of the wire is L. Okay, it is L. Now how to do this? First you have to apply Gauss law. So apply Gauss law, what you have to do, you have to consider what is the total charge enclosed by the surface. So total charge enclosed by the surface is charge per unit length into the length. This is charge per unit length, this is the length, so total charge is lambda into L. Now from Gauss's law, okay, we can write phi equals to Q enclosed by epsilon naught. Now what is the definition of flask? Definition of electric flask is E dot ds equals to Q enclosed by epsilon naught. Okay, now E dot ds is what? E dot ds is basically E is constant on the surface of the cylinder because of the cylindrical symmetry. Any symmetry is there, that means Gauss's law is 100% easier for us to apply, right? So it is because there is a cylindrical symmetry, so E dot ds, definitely E will be constant, it will come out of the integration, and we will get ds inside. Now we will take the magnitude obviously, and that will be Q enclosed by epsilon naught. Okay, now E into what is S ds here? Ds is the area of the curved surface. Area of the curved surface of a cylinder. If you cut the cylinder into from the middle, then you will get a rectangle of this side. The height is obviously L, as usual. This is L. Now if you cut it from here, then what is the length? Length is the perimeter of this circle. What is the perimeter of this circle? Perimeter of this circle is 2 pi r. R is the radius. So what is the area? Area will be 2 pi r into L. So 2 pi r into L is the area. So that will be Q. And what is Qn now? We can put the value of Qn as well. Qn, if you see that Qn value is given here, lambda L. So we will put that value over here. So it will be lambda L by epsilon naught. Now L will cancel from both sides. So we get E equals to 1 by, now we have to little bit rearrange it, 2 pi epsilon naught. If you don't want to do it in one step, you can use one more step, into lambda by r. This is the expression for sorry, I did this derivation in the next part. Okay, I will change the question. Unfortunately the page forwarded, I didn't see that. Anyway, so this is the derivation for question number 41. If you are watching late, then you might see, sir, you are doing a wrong question. No, the question is 41. So this is 41 and we have solved it here. This is question 41. Okay, 42 we will do in the previous part, sorry for that, but when I give you the PDF, I will update the questions, so don't worry about it. Okay, now we will do the 42 here. Okay, we will solve the question number 42 over here. Okay, this is not the question obviously. Now what is the question number 41? Question number 42. 42 is derive an expression for electric field at a point on the axis of an electric dipole. So from all the dipole related questions, axis is the most commonly asked. This is question number 42. As I said, now electric dipole, we will be solving on the axis of the electric dipole. Okay, axial position, very common. There are very few occasions where the perpendicular bisector or the equatorial plane also came, but this is the most commonly asked. So for students who want to pass, obviously this is the question they are expecting, because it is coming almost quickly, as last year also I think this came. So this is the most commonly asked question. So we want to find the electric field at some point P. The distance is obviously r, and the dipole is divided into two halves. One is A, another half is also A. Okay, so we will try to find the dipole moment. How to do, not dipole moment, electric field. How to do that? First, what is the electric field due to the positive charge? Electric field due to the positive charge is E plus. Electric field due to the negative charge is E minus. Okay, so electric field is E plus and electric, this is E minus. Now what? Now we are trying to find the individual values and who is bigger, who is greater. Okay, I think there is a small mistake here. Not mistake, anyway this is correct perfectly, but from the terms of book we will do it that plus charge is facing this point and negative charge is away from it. So which electric field is bigger? Which field is bigger? Who is closer here? Plus charge is closer. So plus charge closer means it is in the direction of plus charge. E plus will be bigger than E minus. Okay, so E plus will be bigger than E minus. Now let us find the electric fields one by one. What is E plus? So E plus is basically, let me start from here as well only. Okay, so E plus is what? E plus is KQ by the distance. What is this distance? This distance is, total distance is R, okay, minus A is this, so R minus A whole square, KQ by R square, that is the formula, but here the distance is R minus A. What is E plus? This is E plus. What is E minus? E minus is KQ by R plus A whole square. These are the two electric fields. Now what is the total electric field? Obviously we know that this is greater than E minus, so net electric field will be E plus minus E minus. They are opposite direction, right? E plus is in this direction, E minus is in this direction, so definitely they will be in opposite direction, so the net electric field will be subtraction. So now we have to put the values. So KQ by R minus A whole square minus KQ divided by R plus A whole square. Now KQ you can take common, okay, now this will go up, R plus A whole square minus this will come here, R minus A whole square, in the denominator they will multiply, R minus A whole square into R plus A whole square. Now what I will do, instead of writing it like that, I will take the square in both the terms as common, okay, square I will take common. Sir, how can you take square common? I can take square common like this, right? I can take square common. So now is the magic. So KQ. What is A plus B whole square minus A minus B whole square? If you don't remember, I am telling you the formula. It is 4AB. 4AB. Okay, A plus B whole square minus A minus B whole square. If you don't remember the formula, you break this into terms in the rough and then add them, you will find A plus 4AB. Okay, 4AB means 4R into 4A. And this is easy, A minus B into A plus B, or A plus B into A minus B, that is A square minus B square. Here whoever is plus, that will be first, and minus will be B square whole square. The whole square common will still be there, so don't miss out any of the terms over here. So this is the net electric field we have calculated. Now there is a catch. What is that? That is, first of all, we have to say that the value of A is super small, such that this is very, very smaller compared to distance R. Why? Because this is a dipole. In case of dipole, the dipole is defined by the two equal and opposite charges separated by a very small distance. So this distance is very, very small, so that means A should be very, very smaller than R. So what we can write, we can ignore this A square but not this A. The upper A we will not ignore, the lower A we will ignore. Why? Because A is smaller, that means A square will be super duper smaller, right? So if you do a square of a smaller number which is less than 1, for example, it becomes much more smaller. For example, 0.1 square is 0.01. 0.01 is much smaller, right? So smaller number becomes smaller when you square them. So now net electric field will be Q into 4RA divided by this one we have ignored, so R square whole square. R square whole square means R to the power 4. Now if you see, there is one R here as well, so one of them will cancel, and then we will do some rearrangement. How to do rearrangement? 2K, one of the two, Q into 2A divided by R cube. Now Q into 2A is called the dipole moment. So it will be, now K is 1 by 4 pi epsilon naught. This quantity is called dipole moment, so there will be 2p divided by R cube. So this is the expression for net electric field. Now in terms of vector form, this will be vector, this will be vector, and as you can see that electric field is in the same direction as the dipole moment. Dipole moment is defined by the term called Q2A, and also it is multiplied, its direction is from negative to positive charge. Okay, its direction is from negative to positive charge, right? Let's move on. Obviously this is the question number 42 I have done now. Those who are joining right now and thinking, sir, what are you doing? So by mistake I solved question number 41 in 42's place, and 42 I had no option to solve it at 41's place. Now arrive at the balanced condition of the Wheatstone bridge using Kirchhoff's rules. So this is also very important question. So we have sometimes I have seen only once, I think in 2023, they asked that draw the circuit diagram for Kirchhoff's law and mention the condition for balance. Okay, so they don't ask you to derive it. So derivation is not required. You just gave you as a 3 marker or 2 marker question. They just ask you what is the condition of balance. Then you just need to draw this circuit diagram and write the final expression that we are going to write. Okay, but if it is coming as a 5 marker derivation, you have to do the derivation. So there is a current I1, there is a current Ig going through this, there is a current I1 minus Ig. Okay, there is a current going through this is I2, say Ig is going, so through this it is I2 plus Ig. Okay, so this is the Kirchhoff's current law already applied in the circuit. This resistance is P, this resistance is Q, this is R, this is S. Okay, now I will going to teach you, I have done this multiple times. Today I am going to do it in a different way. It's a little bit shortcut way. What is that? That condition for balance is Ig equals to 0. So we will start with this, okay, and then we will apply Kirchhoff's voltage law. So Kirchhoff's voltage law means what we will do, you will put Ig equals to 0 from the beginning, so we will ignore anything which is related to Ig. Now we will apply the law from here, here and here. This is our first loop as usual. So we will start from here, A, B, C, A. This is say D. Okay, so we will A, B, C, A. Loop A, B, C, A. This is our first loop, and in this loop, what is the first? We are going from here to here. Current is I1, resistance is P. So I1 into P plus. Now, well, we are going from here to here. As I have written, Ig is 0. So G will not create anything in this equation. Second is we are going from here to here. That means Q into I2. So Q into I2 equals to 0. So from there we can write P by Q equals to, there is a one more thing, there will be negative sign. My mistake, this will be negative. Why this is negative? Because current is passing in this direction, we are going in the opposite direction, so this is negative. So I1P equals to QI2, or P by Q equals to I2 by I1. Sir, can I do this way? Yes, you can do this way. This is the first stage, equation number 1. Now what is the second loop? Second loop we will use CDBC. Okay, second loop is CDBC. Okay, this is the second loop, and in this case we will start from C. We are going in this direction. Now Ig itself is 0. So Ig 0 means only I2 is left. I2 into S. Remember that Ig is 0, so Ig you can even ignore. In this diagram also you can ignore Ig, okay, if you want to. Okay, no need to consider Ig because we have started with the condition for balance where we have mentioned that Ig is 0. Okay, so I2 into S in this direction. Now here we are going in the opposite direction. Okay, we are going like this. Here we are going in the opposite direction, so it will be I1 into R. So minus I1 into R. Why minus? Because as we are going in the opposite direction of the current, it will be negative. Now here the G is 0, so don't need to consider it. So it should be equals to 0. Okay, so from here we get I2S equals to I1 R. Okay, or R by S equals to I2 by I1. We have to match this side. That's why. Okay, so R by S equals to I2 by I1. See, this is equation number 2. If you compare 1 and 2, you can write P by Q equals to R by S. This is the condition for balance. That means no current is passing through this galvanometer. Okay, the resistances are aligned such that no current is passing through this galvanometer. Now if they ask you, draw the diagram and write the condition for balance, draw the diagram, write the condition for balance. That is for a 2 marker or 3 marker question. But if it is coming as a 5 marker question, this is the shortest derivation. That is possible. Okay, for all of you I have done this so that you don't have to remember too much. If you practice it twice, you can still answer it. Now next question, derive the expression for the magnetic field at a point on the axis of a circular current loop. This is very important derivation almost every year, not alternate year, almost every year this question comes. So first of all, obviously we have to consider a circular loop, current through the loop say I, the radius of the loop say R, and we are considering a small element dl over here. Okay, and the point where we are trying to measure the magnetic field is here, which is P. The angle theta in this case is 90 degrees. We will consider another angle phi. Okay, the magnetic field at this point, which will make dB, that will make an angle phi with this. Okay, so this angle is phi. Now only x component will survive, that is dBx. Y components will cancel because of the spherical, because of the circular symmetry. So if you consider another point over here, they will cancel. Now I have explained it multiple times. If you are not super interested in that, you don't need to write it there anyway. You just need to write that x component will survive, y component will not. So from Biot-Savart law, we can write that dB equals to mu naught by 4 pi I dl sin theta by r square. Now sin theta is 90 degree, so sin theta is 1. Now I have seen students and even some books, they use this theta, this as also theta. Two angles having different values cannot have same name. For example, if I say that there are 2 students having the same name, say Rahul in the class, so both of them cannot be the same student. So you have to have, they look different, okay, and their surnames will be different. Even if their surnames are same, they are, we will call them Rahul A, Rahul B, right? Similarly here as well, you cannot call 2 angles same name where they have different values. One of them is fixed 90 degrees, one of them is varying based on the distance. Obviously you cannot call them both theta. I have seen students mark this angle also theta, which is very confusing for the teachers. So mark this angle as phi only. So theta 90 degree sine theta is equals to 1, right? Now what we will do, we will try to calculate the magnetic field. So dB is equals to mu naught by 4 pi I dl by r square. Okay, this is the magnetic field. So what is the x component? dVx equals to dB cos phi. Okay, this is the cos component. X component means x component is always cos component. Okay, so we will put the values now. Mu naught by 4 pi I dl. What is r, by the way? R is square root of r square plus x square. This is a right angle triangle, right? This is a right angle triangle and this is a hypotenuse. So this is from Pythagoras theorem. R is r square plus x square. So r square will be only r square plus x square, no square root, because that is gone. Now what is cos phi? If this angle is phi, this is the base side, so cos phi will be r by square root of r square plus x square. Okay, cos is base by hypotenuse. So this is base, this is hypotenuse, so this is the value. So from there we can write this as mu naught by 4 pi I r comes over here, and in the division r square plus x square to the power 3 by 2 into dl. Okay, so this is the formula for dvx. Now what? Now we have to do the integration to calculate bx. So integration is basically obviously mu naught by 4 pi is constant, then ir by r square plus x square to the power 3 by 2. This is also constant, nothing is changing, only thing that is changing is dl. Close integral dl. Close integral dl means you are taking small elements of this circle and then you are adding it. So what you will get? Small dls across the circle, you will get the perimeter of the circle. What is the perimeter of the circle? Perimeter of the circle is nothing but mu naught by 4 pi. Obviously you have to continue with everything that you have started with. There is no chance of dropping anything at this stage. So perimeter, this is the perimeter, total perimeter. Perimeter is 2 pi r, right? So 2 pi cancels over here. So you get mu naught by 2 I r square. This r will multiply, so I r square plus x square to the power 3 by 2. This is the final expression of bx, or net magnetic field at a point at a distance x from the center of a coil. Okay, this is a longer derivation, but methodical step-by-step derivation. If you follow the steps, you can answer it. Derive an expression for refractive index of the material of a prism in terms of angle of minimum deviation and angle of the prism. So first of all, you have to draw this diagram. This will come next. The below one you can ignore it right now. First you have to draw this prism diagram. Mention I, R1, R2, angle of the prism, the angle of deviation delta, and angle of emergent E. From there you have to write, from geometry we can write delta equals to I plus E minus A. Okay, the geometrical explanation if you want to give, that is fine, but this is you have to write. Okay, and then again A is equals to R1 plus R2. These are from geometrical derivations. Now by observing I versus, now you have to draw this graph. After this graph should come. First you will start with this, then you have to write these two equations, and then you have to draw this delta graph. By observing I versus delta graph, we can see that the angle of minimum deviation occurs when angle of incidence I is equal to the emergent angle E. that is I is equals to E and R1 equals to R2 equals to R. Okay, so what we will do, we will put these values. So delta minimum becomes 2I minus A. Okay, so if you put I here also, I plus I is 2I, 2I minus A, so delta M becomes 2I minus A, or I becomes A plus delta M by 2. Right? Similarly, A is equals to 2R because R1 plus R2 both are equals to R. So R1 plus R2, R plus R, that is 2R. From there you get R equals to A by 2. Now Snell's law tells you that the refractive index of the prism is given by sin I by sin R. So there, from there you can write what is I is A plus delta M by 2, what is R is A by 2. So this is the very common derivation. 2023 this derivation came, might be it will come in your year as well, so that is why I am trying to practice it as well. Now deduce Lenz maker's formula, another very important derivations often comes. So we have to start with a diagram like this. The radius of curvature of this surface is R1, this is R2. Okay, so this is U, and when the ray trying to pass through this and passes somewhere, this is say V dash, this distance is V dash, and after refracting this is actually meet here, this is V. Okay, now while doing the Lenz maker's formula we will not apply any sign convention. Okay, sign convention we will apply while actually doing the numericals. While doing the Lenz maker's formula, sign convention is not required to be applied. Now refractive index of this medium is N1, refractive index of this medium is N2, this is N1 again, back to N1. So first we have to use the spherical surface diffraction formula. Okay, for diffraction through a spherical surface, the refractive index divided by the corresponding distance is very, very important. We start, what is the, you remember the Lenz equation. What is Lenz equation? 1 by V minus 1 by U equals to 1 by F. So we will keep that equation back of our mind. We will not write this equation anywhere except in the rough spaces maybe. But what is the first term? First term is V. Here for this surface we will start with the first surface. So this is U and corresponding V is this. Okay, so and where it is happening? It is happening inside the lens. So the refractive index is N2. So N2 by V dash minus N1 by U. Okay, so U is where? U is located in this medium. So even though this is in back of our mind, when in writing we have to incorporate the corresponding refractive index as well. So N2 is happening inside the lens, so that is why V dash, when we are writing the equation V dash, corresponding refractive index is coming. Similarly U is happening outside the lens where N1 is the present, so it will be N1. That should be equals to N2 minus N1 divided by the corresponding radius of curvature R1. Okay, so this is the first equation, equation number 1. Now when the light is falling on the second medium, second surface, okay, now for this U is this, V dash is the U, and where it is actually in N2, whereas the final distance is V. Final distance is happening where? Final distance is happening outside. So N1 by V, okay, minus N2 by V dash equals to now light is traveling from N2 to N1. So final minus initial equals to divided by R2. Got it? Now if you add them, this is plus, this is minus, they will cancel. You get N1 by V minus N1 by U equals to N2 minus N1. Okay, this is plus R1 by R1. Now if you see that this was opposite, so if I want to take the same thing common, only thing that I have to do, I have to use a negative sign for that. So this is the final formula. So 1 by V minus 1 by U equals to N2 by N1 minus 1 by 1 by R1 minus 1 by R2. So now this is not yet over. For what is the definition of focal length? So focal length is defined when the object is at infinity. When the object is at infinity, image is formed at the focus. Image is formed at the focus. So that is the definition of focal length. So we will put that value over here. So 1 by F minus 1 by infinity equals to N21 minus 1 by 1 by R1 minus 1 by R2. N21 is what? N21 is the relative refractive index of the second medium with respect to the first medium. Okay. So this is again a few things you need to practice. If you have not yet practiced, then go and practice it once more. Now what? Now we can see that 1 by F is there, 1 by infinity is 0. So it will be N21 minus 1 divided into 1 by R1 minus 1 by R2. This is the required Lenz maker's formula. Now there is a chance, very small probability that this derivation might come. It has come in the past, but there is a small chance. I am not doing that derivation. I have done this in the past. I am not doing it in this lecture anyway, because this is most focused, most important and expected questions. So I hope that if you solve all the 10 derivations, 3 derivations definitely you will get common. Using Huygens principle, arrive at the Snell's law of refraction for a plane wave. Okay, that is my target. I am not saying that all the 5 derivations you will get common, but definitely if you study at least these 10 derivations, you will get 3 of the derivations definitely common. So this is the ray of light. After coming to the second medium, it bends and it travels, say, up to this. So this was the incident wavefront. If you draw a perpendicular here, and this will be the refracted wavefront. Okay, so this angle is I, this angle is I, this angle is R, this angle is R. Okay, so this is the refraction. This diagram you have to remember. Speed of light in this medium, say V1, speed of light in this medium, say V2. Okay, so these are the things you have to remember. What else? Time taken by the light to reach from, say, so this is say A, this is say B, this is C, this is D. Okay, AC is incident wavefront and BD is refracted wavefront. So AC is incident wavefront and BD is refracted wavefront. Right now, the time taken by the light, time taken by the light to reach C2D, that is CD, is equal to time taken to reach A to B. Okay, so the time by which light comes from C to D, the same time light reaches A to B. That is the main part, right? So what we will do, we will say that time is equals to T, say. Now speed of light in this medium is V1, speed of light in this medium is V2. So what is CD? CD is basically what is distance? Distance is speed into time. Speed is V1 and distance is time is T. So CD is basically V1 into T, whereas AB is equals to V2 into T. Okay, simple. Now also you have to remember that this is a wavefront, means these angles are 90 degrees. These angles are 90 degrees. Now what do you have to do? You have to find sin I and sin R, because Snell's law talks about the ratios of these two angles. So sin I is what? This is angle I. This is 90 degrees. That means this is hypotenuse. Okay, 90 degrees opposite side is hypotenuse. So AD is hypotenuse. Okay, and sin I is basically perpendicular. So in this case, this is perpendicular and this is hypotenuse. So sin I is CD by AD. Similarly, what is sin R? Sin R will be AB by AD. This angle is 90 degrees, so hypotenuse is same. Now this is the angle R, that means this will be AB will be the perpendicular. Now sin I by sin R equals to CD by AD divided by AB divided by AD. So both has AD division common. So AD will cancel. You will get this is equals to CD by AB. Now what is CD? We have already calculated. CD is V1T. And what is AB? AB is V2T. So TT cancels. Now V1 is happening in the first medium, that is where I is. So what we will do, we will bring V1 with sin I. So it will be sin I by V1. Okay, V1 was here, so it will come back device, and this will cross multiply sin R, and this will be staying with V2. So everything, V2 was with R, V1 with I. So we have segregated based on that. Now what we will do, we will multiply C on both sides. So C by V1 sin I equals to C by V2 sin R. So these are the easier way to remember. That is why I am doing it this way. Okay, I have done it in a higher method also, but this is a easier way to remember. I and V1 in the same medium, so they should be staying together. R and V2 are in the same medium, so they should be staying together. Now C by V1 is refractive index of the first medium, that is N1 sin I equals to C by V2 is the refractive index of the second medium, N2 sin R. This is the generalized Snell's law. So this is how you can prove Snell's law from Huygens principle. Now next two derivations are very simple and easy. That is, what is a rectifier? Explain the working of a full wave rectifier using a neat circuit diagram. Draw its output, input output waveform. So what is a rectifier? A rectifier is an electronic device that converts alternating current AC into direct current DC. Now you have to draw this diagram. This is a full wave rectifier diagram. Okay, this is a full wave rectifier diagram, and during the positive half cycle you have to write two cases: positive half cycle, negative half cycle. Whatever rectifier they give you, if they give you half wave rectifier, also you have to write for two cases. If they give you full wave rectifier, also you have to write it for two cases. Positive half cycle of the AC input. During the positive half cycle of the AC input voltage, the upper half of the transformer secondary windings becomes positive. So diode D1, so this is positive. So this is positive, this is negative, that means diode D1 is positive. So current through the resistance, so current, this diode conducts, so diode conducting means current passes through this way. This is the possible path. So current passes from X to Y. So diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistor RL. Diode D2 is reverse biased and does not conduct. Now this is negative, this is 0, so definitely no current will pass from negative to 0. Okay, reverse biased. Now now negative half cycle, what happens? During the negative half cycle of the AC input, voltage of the lower half of the transformer secondary windings becomes positive. Diode D2 becomes forward biased and conducts, while diode D1 is reverse biased and does not conduct. Current again flows through the load resistor RL in the same direction as during the positive half cycle. That is, you get this is the input wavefront, this is the output wavefront, this is the shortcut circuit diagram. Okay, and whenever you are drawing the circuit diagram, you have to show this dotted line, obviously. So this is the shortcut form of the diagram. You can draw the bigger diagram given in your NCERT book, but this is the smallest possible diagram. Okay. Now what is a half wave rectifier? Explain the working of a half wave rectifier using a neat circuit diagram. Also draw input output waveforms corresponding to it. So half wave rectifier is an electronic circuit that converts alternating current AC into direct current DC by allowing current to flow only during one half cycle of the AC input signal. The outer half cycle is blocked, so only half of the AC wavefront is used. Okay, so this is the half wave circuit diagram. Now during the positive half cycle of the AC input, the P side of the diode is positive with respect to the N side. The diode becomes forward biased and conducts current. Current flows through the load resistor RL in one direction and the voltage across the load is positive. During the negative half cycle of the AC input, the P side of the diode becomes negative with respect to the N side. The diode is reverse biased and does not conduct. No current flows through the load resistor RL and the output voltage is 0 in the half cycle, and this is the circuit diagrams. So if you follow these steps, definitely you will score 40 plus marks in your PU exam. Okay, don't take too much stress. Answer the questions which you feel you are comfortable with. Also the first half, 1.5 pages you should reserve, possibly first 2 pages you should reserve for MCQ and fill in the blanks. Then you should start with other groups, group A, group B, group B, group C, group D. Okay, if you want you can change the order, but always remember that try to write the entire paper at same place. If you are writing group B, try to write all the group B at a same place, one after another. If you don't think that okay, I might not be able to answer the question, leave some space, come back later, write it there. Okay, and leave enough space, you will get enough number of pages. So leave enough space so that you can write the answer completely in that space. Okay, very important that you follow these steps, and I wish all the best for your upcoming PU exam. I will see you again another live session tomorrow. Till then, bye.